All right, welcome to the second portion of section 8.1. We're going to be looking at these last 6 slides, and what we're going to be talking about relates to what we did in the first half of section 8.1. But now we get to what is called summation notation. So when we're talking about summation notation, the thing that we're going to write about it is that it's the sum of the first n terms. So the sum of the first n terms, where n there is a variable, of a sequence. Whoa, awesome spelling on sequence, Mr. Davis. Sequence, promise I know how to spell that, is represented by, represented, okay, I got my spelling down. So the sum of the first n terms of a sequence is represented by, and then pay attention to how we sort of write this. So you're going to have this E looking thing, and I'm actually going to fix that a little bit. I won't be too particular about it. I just needed a little bit more space down here. This E is called sigma, and what it represents in math is going to be the sum. So it represents the addition of a whole bunch of terms. And this is going to be the sigma, or the summation from I is equal to 1 up until n of a sub I. And what this really means is that we're doing a sub 1. Okay, well, there's an A here. It's just not showing up. Let's fix that a little bit. A sub 1 plus A sub 2 plus A sub 3 plus, and so on and so forth until we get to A sub n minus 1, so a term less, and then A sub n. So whatever number up here, that's telling us where we're going to be stopping. So I here, I is called the index of the summation. What n is called is the upper limit of the summation, and 1 is the lower limit. That's essentially telling us where are we going to be starting and where are we going to be stopping. So notice when we're talking about a sub I, what that's really telling us is all those terms that we dealt with. So in the first part of 8.1, we dealt with writing sequences. Now we're essentially saying a sub I is the sequence, that formula. And when we take the sum of it, we're just saying now we have that sequence, we're going to add all of those terms together. So as I said, in this case, we are going to do the examples with us, or with you. I'm going to do them with you. There we go. So here, we're saying that we want the summation of 2I, starting at I being 1 up until I is 5. So I will show all the work in this case. You wouldn't necessarily always have to, although it's generally relatively recommended. So we're doing 2 times I being 1. That's 2. Plus 2 times I being 2. That's 4. Plus 2 times I being 3. That's 6. Plus 2 times I being I being 3, I being 4, and I being 5. 8 and 10. I'm stopping at I being 5 because that was my upper limit, which tells me when to stop taking the sum. When I add all these together, I get 30. My answer just regular 30. The summation from 1 to 3 of I squared means that I'm doing 1 squared plus 2 squared plus 3 squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, so this adds up to 14. Notice, unlike a sequence question, the sequence is when you're writing out the actual terms, 1, 4, 9. A summation is when you're just saying, now that we have that sequence, add it all together and see what we get. Notice these next two are the same. That's by accident. You can just cross this bottom one out. I double crossed that for some reason. I might as well be consistent. So looking at this first one, here is a situation where it might actually be helpful to write all of that out, or not it might, it is helpful to write it all out, because you're going to realize that you're going to get some different fractions, and you have some oscillating signs, changing signs back and forth. So when I'm starting at 3, I'll have negative 1 to the third over 3 minus 1. And negative 1 to the third, all that's going to do is give me negative 1 over 3 minus 1 is 2. My next term, so I'm adding, this is going to be negative 1 to the 4th over 4 minus 1. Now, right away, we can realize, okay, so the denominators, it's just going to be going down by 1 each time. So I know I'm going to be having something that's over 3. Then I'll have something that's over 4. Then I'll have something that's over 5. Then I'll have something that's over 6. And that's when I'm going to stop, because my upper limit is 7, which doesn't mean that I'm going to have 7 terms or the last one will be 7. It just means 7 is the last thing that will be substituted in. And when I substitute 7 in for this, I'll have 7 minus 1, which is 6. So that's why I'm stopping there. In terms of my numerators, you can recognize a pattern. Negative 1 to the 3rd will just give me negative 1. Negative 1 to the 4th will give me positive 1. Negative 1 to the 5th, which is what would be here, well, all that's going to do is keep changing this between negative and positive. So I'll have minus 1, plus 1, minus 1. Now, I do want the sum of all this, which means I want a common denominator between 2, 3, 4, 5, and 6. My common denominator there, and it's sort of cool how I'm going to show this, the common denominator between all of these is going to be 60. So if you talk about 60ths, to turn 2 into 60, I'd be multiplying by 30. So this is a negative 30. Notice, negative 30 60ths is negative 1/2. 1/3 of 60 is going to be 20. 1/4 of 60 is going to be negative 15. 1/5 of 60 will be positive 12. And negative 1/6 of 60 is going to be negative 10. Now all I do is add this whole numerator together to get me negative 23 60ths. It doesn't reduce at all, so I can leave it just like that. That's a terrible box. It's also a terrible 60. So sorry. There we go. Okay, it's still a bad box, but at least the 60's there and nothing's being written on top. So negative 23 60ths. Again, we're getting not integer answers, but we're getting values. We're not getting some sequence or some pattern. We're not writing an equation. We're just getting the actual sum of all of this. So in certain scenarios, we can actually speed some of these up, or we have ways of sort of rewriting these. So if we have C representing a constant, so some integer like 5, something that's not going to change dependent on what I is. If we have the sum from 1 to n of C, then all we're doing is adding C over and over and over and over and over again n times. So that can be found by just doing C times n. I'm adding C n number of times. If I have the summation of 1 to n of C times a sub I, meaning there is some sequence here that depends on the index, what I can do is factor that constant out and multiply by the sum from 1 to n of a sub I. So that one just allows us to pull the constant out of this and take the sum of the actual thing that is changing on its own. The next two, very similar to each other. It's sort of, I mean, it's not the distributive property. It's not. I'm not distributing sum, but it will appear in the same way, which is sort of nice. If I have the sum of two sequences being added together, what I can do is take the sum of one sequence from 1 to n, so of a sub I, and then I could just take the sum of the second sequence from 1 to n of b sub I and add those separate sums together. So I don't have to actually add the formulas. I can find the sum of one, the sum of the other, and add those together. Same thing with subtraction. So now I can say from I being 1, you'll notice that my sigmas will get progressively less pretty. This, super pretty. This, I don't know what happened down here. This, it sort of looks like it's opening up to eat something. And now it's not even really sigma looking. So I won't be super critical about you guys. But naturally you'll, oh, look, that one wasn't bad. You'll be critical of mine, so I'll still be a little bit critical of yours. All right, so just some rules to remember that help us rewriting and stuff. So determine the summation notation. Now, these are questions that can be tricky. What you're doing in these is you're trying to write the summation notation. So for all of these, we can start off by saying, okay, this is going to be the sum, that's not sum, I don't know what that is, and the sum. Okay, less pretty. And then what you're trying to do is sort of like in the previous day or the previous lesson when you guys had to write the sequence formula. Right here, you're trying to write the formula, but then you're also saying where does it start and where does it end? And sometimes there's a couple ways that we can write this. So looking at this first one, what I look at is in between all of these terms, so term 1, 2, 3, these are my I values. So I can realize that the numerator is not changing, which means I'm going to keep this as 2 over. And then what I realize about the denominator is the only thing that's changing is what I'm adding in the denominator. And what you can realize is what you're adding is whatever the term is. So here I added 1, which was the term number. Here I added 2, which was the term number. So this is just 1 plus whatever the term number is. That's starting at 1. And then it's ending right here, which would be at 8. So that's how we write that first one. And that's all we're doing there. We're not actually finding the sum. It doesn't ask for that. It just asks for the summation notation. For our next one, again, I have a little bit of a fraction here. I usually would try and think of that. Okay, so this is 1 over 1. So here's my I equals 1 term, 2 term, 3 term, 4 term, and I don't exactly know what term that is yet. So when I'm looking at these numerators, you can realize that it's always 1. However, the sign is changing. Here it's positive, here it's negative, here it's positive, here it's negative. So the only way that the sign changes, but the value doesn't, is if sometimes you multiply by positive 1 and sometimes you multiply by negative 1. So we're going to write this with a negative 1 to the power of, and it has to be in parentheses, noting that the negative is sometimes going to be to a positive or to an even or to an odd exponent. And then to decide whether or not this should just be I or I minus 1, you look at that first term. So if I is 1 here, well, my first term right here is just positive. So if I write this as just negative 1 to the power of I, negative 1 to the first power would give me negative, and I need a first term that's positive. So I'll change this and say minus 1. Now, if I were to substitute that 1 in, I'd get negative 1 to the 0 power, which is still positive 1, which would give me that numerator, positive 1. All right, so numerator, done. Usually it's good to check a couple of these. So like if I substitute 2 in for this, negative 1 to the first power would give me negative 1, and here's my negative 1. Then with my denominators, I've got 1, 2, 4, 8. What I can realize about this is it is exponential, and it's an exponential with a base of 2. So here, this is 2 to the first power, 2 to the second power, 2 to the third. So this is 2 to the first, 2 to the second, 2 to the third. So if I compare the term number to the exponent, realize that the term number is larger by 1. So this is 2 to the power of I, but whatever the term number is, like in this case, it's 3, I have to subtract 1 to get that exponent. So it'll be I minus 1. In this first case, this is 2 to the 0 power. So if I check to that real quick, 2 to the 1 minus 1, that's 2 to the 0, which is 1. If I check the second term, 2 to the 2 minus 1 is 1. So 2 to the first is 2. You can check that throughout. It always works. Now you got to think about 128. 128 is 2 to the 7th power. And this right here is what usually gets people. They always then say the upper limit is going to be 7 because that's the exponent. But the upper limit has to be what I value did I substitute into this to get 7. And in this case, because I'm subtracting 1 from it, that means that my upper limit must be 8. That's a terrible 8. It's not very clear. 8. I still don't like that. Make it nice. There we go. Okay, that's sort of a good 8. There we go, summation notation. Upper limit, lower limit, and then the actual equation. Expression. All right, next one, not as bad. The numerator does have something that's a little bit different for us. I'm just looking, there we go. We'll start with the denominator. It's a little bit easier. Here I can see that this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and 2 to the sixth. So right away I can see, okay, I have 6 terms. Notice I didn't have this dot, dot, dot. So it's ending right here. 6 terms, starting at 1. And in the denominator, what I have is 2 to whatever I is. So it's 2 to the power of I in the denominator. In the numerator, we have 1, then 2, then 6, then 24, then 120, then 720. So obviously I'm not adding the same thing, nor am I multiplying the same thing. But you could say, okay, right here I multiplied by 2, then I multiplied by 3, then I multiplied by 4, then by 5, then by 6. And some people sort of struggle with, they see it, but they're not sure how to exactly write that. And if you've seen that before, what you are doing but not realize that you're doing is actually a factorial, that little exclamation point that we talked about previously. So 1, this is 1 factorial. 2 is 2 factorial. 6 is 3 factorial, because in 3 factorial, what I'm doing is 3 times 2 times 1, which is 6. Now this is 4 factorial, because I'm going to take that 6 and I'm just going to now multiply it by 4. This is 5 factorial. So you're comparing the factorial to the term number, and you see that this is just I factorial. Whatever the term number is, I take that factorial and I get the numerator, the 6 factorial. We'll have some more fun with these. These are always a good time. Generally not too bad. You just get some of these trick things like that exponent, or factorials are a little bit tougher to see sometimes. All right, determine the nth partial sum. The nth partial sum means we're stopping at the upper limit. In this case, the upper limits just say infinity, but I'm telling you which term to stop at for each problem. So we have the sum of 2 times 1/3 to the power of I, from I being 1 to infinity. So this is an infinite sum right now, because it continues on infinitely, but we're going to take the partial sum of it, meaning we're going to take a finite piece of it. First thing I realize is this 2, that's just a constant, so I can factor it out. So this is going to be 2 times the sum of I being 1, and we're going to stop it at 3, of 1/3 to the power of I. So when I substitute in these I values, I'm going to have 2 times, and when I substitute in 1, I get 1/3. When I substitute in 2, I get 1/9. And when I substitute in 3, my upper limit, I get 1/27. So this is the summation. This was a constant I pulled out of it. Again, between all of these, you just get one common denominator, which in this case is 27. 1/3 of 27 is 9. 1/9 of 27 is 3. 1/27 of 27 is 1. This is being multiplied by 2. So that's going to give me 26/27. So pretty close to 1 right here. For our next one, we're using that same equation, but now we're going to say, okay, let's go to n equals 5. So one thing to realize about this is you already have part of that sum. You already have from n being 3. So you can sort of split this as being the sum, that's a terrible sum, once again, of 2 times 1/3 to I, from I being 1 to 3, plus the sum, it's actually not a sum, that's a set, of 2 times 1/3 to the power of I, but now from I being 4 to 5. So notice I split this as 1 to 3, and then 4 to 5. Because I already knew that from 1 to 3 it was 26/27, I'll change that color to show again where that came from for those of you who are not actually listening to me and just watching. So this 26/27, guys who aren't listening, is going right here. Now I'll continue on with this other portion of this. Just like before, I could factor out the 2. And then I'm going to have the sum starting at 4. So this is going to be 1/81. And substituting in 5, 1/243. When I add those, 243 is the common denominator. This is 3. This is 1. So this is 8/243. Common denominator between these two, keep in mind, all these are is 3 to some power. So 27 goes into 243. This is still 8/243. What I multiplied this was I multiplied 27 times 3 to get 81, times 3 again to get 243. So I'm multiplying this really by like 9/9. It's not a great 9. 9 times 26, just some quick math, is 234. So we get 242/243. We'll show some other ways of doing that. Generally, I'd probably just list out all 5 of them, like 1/3, 1/9, 1/27, 1/81, 1/243, and then I'd get a common denominator between all of them. But I wanted to show you how we can split that partial sum. Now something to realize, 26/27, that's close to 1. 242/243, if that's how you'd say it, is way closer to 1. I mean, they're still sort of arbitrarily small, but what it's important to realize is this is getting closer to 1. In a similar type of problem, now if I ask for the infinite sum, so what we realized in these past two was this 26/27, that was the sum from 1 to 3. From 1 to 5, it was 242/243. But that's just the first 5 terms. If I talk about now the infinite terms, what's happening is this is getting infinitesimally smaller, or infinitesimally closer is the better way of saying that, to 1. So the infinite sum is just 1. And we'll come up later on in the chapter with formulas for infinite sums, but it's good to realize in a case like this, okay, I had something that was close to 1, and if I went further, I had something even closer to 1. So what's happening is I'm just getting closer and closer and closer and closer and closer to 1, but I'm not going to cross it. It's sort of like a quote-unquote asymptote. All right, and this case is a little bit different, but we're going to sort of show you, or I'm going to show you how to use a couple terms to come up with an answer. So an infinite sum of this, I'm going to substitute in 1. I get 3/10. If I substitute in 2, I get 3/100. If I substitute in 3, I get 3/1000. And this goes on, so on and so forth. Okay, so that might be a little bit ugly. Let's think about the decimal. 3/10, that's 0.3. 3/100, that's 0.03. And 3/1000 is 0.003. Now, if I add just these first 3 terms, what I'll realize is I'm going to get 0.333. And as this continues going on and on, I'm just going to keep repeating 3's. Well, 0.3 repeating is also known as 1/3. So my infinite sum of this, if I were to add that up infinitely, I would get 1/3, which means as I'm adding and adding and adding, I'm getting closer and closer and closer and closer and closer to the actual value of 1/3. All right, that's all that we have in section 8.1. What you have to look forward to in section 8.2 is where we sort of break these up into 2 groups, arithmetic sequences and then geometric sequences in 8.3, to talk about some extra features and extra formulas that each one of those has. Make sure you try out a little bit of the homework, and as always, go back to the notes, skip through, see where you have questions, and make sure that you come willing to ask those questions tomorrow.